Hey hackers, Nerdwell here, and today we're going to talk about pulling back the veil to find sensitive data in Android apps. Some of these techniques will be ones that you're probably familiar with, but we'll take a look at some new tools that may streamline your workflow. And some of these techniques may be ones that you're not familiar with, and I hope that you find them useful and that you're able to integrate them into your hacker toolkit. Of course, all the tools and techniques that we're going to look at today should only be used to target apps that you have explicit permission to hack on. And without further ado, let's get started. One of the key benefits of working in an Android environment are the platform level security features that Android provides so that mobile app developers and OEM hardware manufacturers don't have to reinvent the wheel every time they want to implement a security feature that customers have come to expect. And there are a lot of different security protections available in the Android environment, but for this talk we're going to primarily focus on those that relate to information protection. And when we're talking about information protection, especially in a mobile device environment, we can generally break those down into two categories: protection at rest and protection in transit. Of course, in a mobile environment, data protection at rest is especially important because our devices are so small, they're easy to lose. You might even set it down, walk away, and come back, and in the meantime, an attacker can trivially clone your device without you being any the wiser. So Android provides whole device encryption to protect against these types of attacks, but this does not provide any app level protection once the device has been unlocked, which is what we're going to take a look at today. Another key security feature that Android provides for data at rest is per app isolation. And this is implemented using Linux users, where each app has a user assigned to it under which it runs, and that app user has its own folder internal to the device that only it has access to. So application A cannot access application B's data and vice versa. And this is critical to keeping the scale of a compromise limited to one app, so that if app A is compromised, it cannot access the data from app B. For data protection in transit, we generally see this implemented using TLS to encrypt the traffic. And increasingly, we see the use of certificate pinning to require a very specific certificate to be presented to the mobile app by the back-end server. And at a high level, the way certificate pinning works is that the app has the public key of the cert that it expects to receive from the back-end API. And even if the API provides a certificate that is signed by a trusted CA, if it is not the specific cert that our app is expecting to see, it will assume that the API is untrusted and will not allow the connection. Of course, this poses some problems if we want to gain a man-in-the-middle position to intercept the traffic for bug bounty purposes. And there are a lot of talks about this, but we'll take a look at some new tools for how we can quickly remove certificate pinning from apps. Before we dig into the technical details, let's take a look at some strategic level bug bounty considerations. And at a high level, the way I approach most bug bounty is that we as bug bounty hunters are attempting to find and invalidate assumptions. And I think you could pretty much break down any vulnerability that you find to some assumption having been made that was either erroneous or did not consider all the possible conditions. And as a hacker, we find some set of conditions that invalidates that assumption with a security impact. So applying this very high level approach to mobile apps, especially Android mobile apps, let's take a look at some common developer assumptions that we might be able to invalidate. First, and while this seems simple, it surprises me how common this tends to be. Sometimes developers assume that the attacker does not have access to the application source code. Another somewhat common developer assumption is that an attacker cannot access private app data. And this relates back to the per app isolation that's provided by the Android platform level security features. And this kind of stems from a misunderstanding of the scope and nature of the protections. And as a bug bounty hunter, we will see if there are ways that we can take advantage of these misunderstandings to achieve a security impact. And lastly, there tends to be an assumption that TLS and certificate pinning prevents all man-in-the-middle attacks such that we are unable to intercept the traffic as a bug bounty hunter. And so let's take a look at some possible ways that we can invalidate these assumptions to achieve a security impact. Let's start with the first, that an attacker does not have access to application source code. Of course, Android apps, for our intents and purposes, are basically specialized Java apps, and there are a number of tools that enable us to trivially reverse the Android APK into human-readable Java or Kotlin code. And we will take a look at how we can potentially exploit this to find secrets within the app itself. The next assumption is that attackers cannot access the private application data for an Android app due to the platform level per app isolation security features. And so we're going to take a look at how we can augment any app that we can download from the Google Play Store to allow us to view the internal private app data of that application to see if there are any secrets within that storage area. Next, the assumption that TLS and certificate pinning cannot be bypassed has long been invalidated, but we're going to take a look at some new tools today that streamline this process significantly and help reduce the errors that we might encounter using the old methods. Now, before we start hacking on our Android apps, we will need some basic tools, both in terms of hardware and software. So, taking a look at the hardware tools that we're going to need, first, of course, we're going to need to have a test Android device. And I actually recommend to have at least two, sometimes more, because Android apps in many instances implement peer-to-peer communication that, of course, we will want to test. And sometimes you will actually find that security features may be implemented differently or unavailable altogether between different versions of the Android OS. So having multiple phones allows us to test all those different variations. Of course, that can get rather costly if you're using new, nice, fancy phones. So I actually recommend for most Android hacking to use burner phones. You can pick them up from any brick and mortar store or any online retailer for generally anywhere from $29 to $45. So for less than $100, you can get 2 to 3 phones and test all the different variations of the apps that you're targeting. And of course, you're going to need a USB cable to hook this device to your computer. Now, all the tools that we're going to take a look at will run in a Windows environment. However, I think you'll find it easier to work in a Mac or Linux environment, not only because the prerequisites are easier to set up in a Mac or Linux environment, but also the tutorials and other videos that you'll find online generally demonstrate using Macs or Linux PCs. And so it'll be a little easier to follow along if you're using a Mac or a Linux PC. So in terms of the software that we're going to need to hack on our Android apps today, some of these may be familiar to you, some may not, but we'll take a look at each. The first essential tool that we'll need is the Android Development Kit. And that includes especially the Android Debug Bridge, ADB, which we'll make heavy use of today. But I recommend to actually get this through the Android Studio. And the reason is, in addition to providing you with all the Android Debug Kit tools, Android Studio gives you a nice user interface to interact with some of those tools, and it makes it easy to do things like take screenshots and take videos, which you will need to do if you do find a vulnerability and you're writing up your report. You will find those to be especially helpful. But it also allows you to open up APKs and inspect within them and even make changes to them. and also to build your own Android apps. And I mention that because anytime you're wanting to break something, which as bug bounty hunters, that's basically what we do. We're breakers, right? It's easier to break something if you understand what the maker is facing when they built that product. For instance, if an Android developer is going to implement a particular feature, they may encounter some common pitfalls, and there are some common approaches to overcoming those pitfalls. And as a developer, they may not know all of those options, or they may not implement them all correctly. As a hacker, if you know what the challenges will be facing an Android developer and what those potential options are and potential pitfalls are, then it just gives you that much more insight to guide your Android hacking activities so that you can get the maximum return for the investment of your time. The next important tool that we'll need today is actually a Java tool. It's called Key Tool, and we're going to be taking apart and repackaging APKs, and so we'll need this to sign them in order to be able to install them on our mobile device. Along the same lines is a jar file that provides APK tool, and this basically lets us quickly and easily depackage and repackage APKs so that we can reverse them and make changes to them and then redeploy. We will use the Uber APK signer to re-sign our packages in some instances, which will take away some of the mundane steps. We can do this without the Uber APK signer, but the steps are actually a little bit different from one version of Android to the next, and it can be a little bit cumbersome and error prone to do it manually. So by using this, we get a one-liner that handles all of those variations for us and lets us quickly and easily repackage, re-sign our APKs for deployment to our mobile device. And lastly, we're going to take a look at a Node.js package called APK-MIDM, which eliminates all the challenges of removing certificate pinning from a mobile app. None of these tools are tools that I have created. They're all created by other people, and we will give appropriate shout outs as we address each one. So where this demo starts out is basically, let's assume that we have an app that we have downloaded from the Google Play Store. It's obviously therefore a release mode app, and we want to strip certificate pinning. Let's say we don't have the APK, and we want to figure out how we can pull the APK, strip certificate pinning, and intercept our traffic. So the first thing we'll want to do is use ADB shell to run pmlist packages. And in this case, I know the name of the app, so I grep on that. And what we'll find right here is that we have the physical path to the APK that is associated with that app package. So we're going to ADB pool that APK. And then we're actually going to go ahead and uninstall that app because we're going to strip certificate pinning and reinstall it. So we'll have a different APK, and if we don't uninstall it first, we will have a namespace conflict when we do so. So now stripping certificate pinning with this tool is as easy as running APK-MIDM and passing it the base APK that we just pulled from the device. It's going to run through a series of steps. We'll wait for that to complete. And when it's done, it will output a base-patched.apk file that we can redeploy. And now we will simply sideload this to our mobile device with ADB install. And there we go. So at this point, we can configure our proxy in the Android system settings and intercept our traffic. Of course, you'll need to trust your burp certificate and all that good stuff. I'm not going to cover those steps in this talk just because they're so well documented. We'll spend our time on some more valuable stuff. I did go ahead and let the app run in real time. I did not speed that up, just so you could get a feel for how quick it is to remove certificate pinning from an app now. It used to be, again, a rather cumbersome and manual process, and as you saw here, it was a piece of cake. I've also noticed that this tool will work on APKX files, and I have not encountered any Android app that it did not work on. So hopefully you will find that useful and you can integrate it into your workflow to speed up the process and automate some of the tasks. Next, let's take a look at that second developer assumption that an attacker does not have access to the app private data. And this can reveal all sorts of interesting information. And so to demonstrate this, I'm going to use that same Android POC app that I created. And basically, it just opens up a web view, hits a web page that I'm hosting, and that web page has some very basic JavaScript that creates a cookie. And the native web view in Android stores cookies using a SQLite database in the app's internal storage. And we'll take a look at how we can view that content. Of course, that's a very simplified demonstration, but I'll talk about how that has actually led to some bugs in my own experience later. But before we go on, let's just touch on one thing, and that is when we're talking about assumptions, it's important to realize that as attackers, we can also make some invalid assumptions. For instance, we might assume that we have access to the application source code and we have the ability to intercept all the traffic using something like APK-minimum to strip certificate pinning. And with those two tools, you should be able to see all the data that the app has within itself from, out of the box, and also any data that it's receiving from back-end server components. And with that, you would think that you could see any sensitive data or hard-coded keys or tokens and that kind of thing. However, there are definitely some instances in which it's easy to miss. And a couple that come to mind that I've encountered in the past are compressed files. So sometimes you will find that data coming from a remote API endpoint is compressed in a way that makes it easy to miss the fact that there's some sensitive data in there. And then also it may even be encrypted beyond the transport level encryption provided by TLS. It may be some encrypted zip file or something. And while it is theoretically possible that you could find the key and decrypt and uncompress that file to find any secrets, it's easy to miss. And so by looking at the private app data, where it sits, where the app is interacting with it as it runs, it just gives us another avenue to find some of that information. So what we're going to do here is basically launch this app that is running on my test mobile device. And as you'll see, it just opens up a web page. And so what we're going to do is similar to the previous demo. We're going to assume that this app is one that we have downloaded from the Google Play Store and that we don't have the APK, that it's a release build of the app, and we want to do whatever we need to do to gain access to the internal app data store. So the first thing we're going to do is similar to the last demo. We're going to list all the packages on the device, and in this case I know it contains the word Nerdwell, so I grep on that. But before I pull it from the device, what I'm going to demonstrate is if we run ADB shell and get to a shell on the mobile device, we can run as the name of the package. And what this would do is allow us to switch to the user context under which that app runs. And then once we're in that user context, we can access that app's internal application folder. However, because this is a release build of the app, we receive this error message. So what we're going to demonstrate is how we can circumvent that to gain the access we seek. So we will go ahead and ADB pull our package from where it physically resides on the mobile device. Then we'll uninstall the app because, again, we're going to make some changes to it, repackage it, and redeploy it. And if we don't uninstall first, we'll have some namespace conflicts when we attempt to do so. Okay, so now we will use the APK tool to decompress that APK and reverse it to editable code. And for this, we use the APK tool D command. We specify the -O flag, which points to the folder that we want to output the contents to, and then we specify the base.apk as the input APK we want to work with. And so now if we take a look at the extracted APK folder contents, we can see this is what's inside that APK. So we will, in this case, we're interested in editing the Android manifest.xml file because this debuggable equals true flag is what we want to change. Now, in most release build apps, you will not find the debuggable equals true flag there in the actual Android manifest.xml file. However, if it is not present, it defaults to false. I put it in this one just because I wanted to make it easier for us to demonstrate. But if you were doing this on a live app that you got off the Google Play Store, basically you would add that whole debuggable equals true in quotes to this file. In this case, I'll just change false to true, save the file, and simple as that. Now, we're going to rebuild this package and redeploy it. But to do that, we're going to have to re-sign it. And so we need to generate a Java key store to do so. So for that, we will use the key tool, and we're going to generate a key store. There are a couple important bits of information that we provide this command that we're going to need to reference here in a minute. And that is the physical file, which in this case is resign.keystore, and then also the alias name. So we'll want to remember those. And then it's going to ask us to enter a password here, and obviously we'll need to remember that because we're going to have to provide it. At this point, we're going to specify some information for the cert. We could hit enter, 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 and move through here. Unknown is perfectly fine for each of these fields. However, on the last entry here, if you just hit enter, it defaults to no and puts you in a loop. So I always just fill them all out because that forces me to remember to type yes. Okay, so now we have our key store generated. What we're going to do at this point is rerun APK tool with the B command to rebuild our APK from the extracted APK folder that we were working in. So in this case, we specify -O for the output to be the APK name of our new APK, and the input is the extracted APK folder that we want to build from. Okay, once that's finished, we will use the Uber APK signer to sign and prepare this package to be deployed. We will specify as an input our APK file that we just generated and the key store that we generated in the prior step. Now, as I mentioned, you will need to know the file name, of course, and then also the alias name. and it will prompt us here for the password. So we will type that in, and just like that, we have a patched, signed, ready to deploy APK. So as you can see here, we have 3 APKs. The first is base.apk, that's the original that we had pulled from the mobile device as it was downloaded from the Google Play Store. The second is --debuggable, which is the one that we created using APK tool with our modified Android manifest file that allows us to debug the app. And lastly is the one that we're actually going to deploy to device, which is the debuggable, aligned, and signed APK. So we can go ahead and install that, side load it by adb install. Okay, so now we will go ahead and rerun the app. Again, all it does is open up this page. But what we're going to do is take a look at the internal storage and see if we can access it now. So we adb shell to get to a shell on the mobile device. We use run as in the app package name to switch context. And as you can see, now we can actually successfully run this command. It actually puts us into the apps folder to begin with. And if we take a look, boom, this is the internal app data. Now, as I mentioned before, this is a standard app view, and a cookie is set using some JavaScript. So let's take a look at this cookies SQLite file, and we're going to dump it with XXD to view the contents. And again, this is running on the Android device. So if we take a look here, looking at the header, it's a SQLite database. And if we scroll through towards the end, we will find the cookie key value pair. Now obviously this is not the most user-friendly format to read, and if you're going to try to demonstrate like a POC for a report, it can be somewhat cumbersome to walk the triager through this whole process. And so in our next demo, we're going to take a look at how we can streamline this. But for this particular use case, all we're demonstrating is this is how you would take a release build APK from the Google Play Store and allow yourself to view all the internal app data. And you'd be surprised what you might find. Anything from Firebase keys that are improperly secured on the back end, to other cloud services tokens that give you access to the remote endpoint servers themselves, to other API keys, or potentially unencrypted PII or PHI. The possibilities are endless, and your mileage may vary from one app to the other. But this gives you a tool that you can use to explore that data. Let's take this a step further. In the last demo, we examined how we can gain access to the internal app data for our POC app. However, we could only view it in the context of the mobile device adb shell itself. And so the tools available to you in adb shell are rather limited. And while you can copy some tools over there and run them, because it's simply a Linux environment, there are some issues there and potential limitations. It would be much easier and much more beneficial to our hacking workflow if we could pull that whole folder over to our Mac or Linux PC and have access to the full scope of our hacking tools and even simple Linux tools that may allow us to more easily extract information or search the contents of that folder for sensitive data. And so in this demo, we're going to pick up where we left off and demonstrate what are the challenges that we might encounter trying to extract that data, and how can we overcome those challenges. So We're going to start by switching to the mobile device shell and changing context to the app user associated with our POC app. And what we're going to do is see if we can make any changes to or view the external storage of the device, which in this case is SD card. And what we're going to find is that we're not able to do that. So as the context of the app user, we are unable to copy the contents of our internal data to our external storage. And I have found this applies even if the app has the right external permission. So while we now have access to the data itself, we don't have the ability to copy it off of the device using simple means such as placing it on the SD card. And basically what our goal is to be able to access this data in some context other than the app user itself, which is what we will need to be able to pull it off the device. So what we can do is, in the context of the user itself, we will tar the contents of the internal app data folder, and we will place that tar file in that same folder because that's the only folder we can write to. So, fortunately within ADB shell we do have access to tar, so we will go ahead and do that, and as you can see, in that folder is our tar file. And I'll just demonstrate here the context that we're running in. As you can see, is the user associated with the app, and we are in the app's internal storage area. So let's go ahead and exit out of ADB shell, and now we're going to be back on our Mac or Linux PC. So what we're going to do here is a handy trick. We can pass ADB shell the commands that we want to run on the device. So in this case, we're going to say launch ADB shell, and then once you do that, I want you to run as the Nerdwell POC app. And then, once you're running in the context of the app user, I want you to run xxd, which is the binary data dump of my tar file. Go ahead and close the quote, and we're going to pipe that to, now this is running on our Mac or Linux device, xxd-r, which reads the contents of xxd output, and we're going to redirect that to a file on our local machine. So just to kind of simplify and reiterate exactly what's going on here, the portion highlighted or underlined in red is running on our Linux device. The portion underlined in green is running on the Android device. And likewise, this last portion in red is also running on our Linux machine. So what we're doing is we're running ADB shell on our Linux machine. We're passing it everything in the quotes to tell it run this on the mobile device. And then we are redirecting the output to something else running on our Linux device. And this xxd-r command is helpful. It's relatively new to the xxd tool itself. But what it does is read the output of a prior xxd command and redirect it to a file that we specify. So in this case, we're going to redirect to a tar file on our local machine. And with that, we are now able to read our internal app data as the user that we need to, and able to write it as a different user. And so now once we have the file locally, we will simply untar it. And because tar keeps the source folder structure, we will have basically that structure created within our current working folder. So what we're going to do now is demonstrate how this can be beneficial to us. In the prior example, we were able to review the cookies SQLite database using on-device tools like XXD, but it wasn't in a very user-friendly format. And as you might imagine, once you start adding a lot of cookies and a lot of other information to some of those files, it can get rather tricky and cumbersome to identify useful information, let alone extract it in a repeatable process for a bug bounty report. And so what we're going to do here is, now that we have the data on our Linux device, we're simply going to use the tools available to us in this more powerful environment, like Python and the SQLite module, to more readily review the data. And so in this case, we're going to open up that cookie database using SQLite module. And just to demonstrate how you might integrate this into your workflow, let's just say we didn't know the exact structure of this SQLite database that we're taking a look at. Well, what we could do is create a query to query the tables, the schema of this SQLite database. So that's what we're doing here. We're going to craft our query, iterate through the results, and print the tables. And here we go. And as you can see, we have one table here that includes all the headers for our cookies table. So now we can see the same data that we saw before in a much more usable format by selecting all from that table. Iterate through the results, print them, which in this case is 1. And as you can see, now we have a much more user-friendly output of the key value pair. Now, again, this was a demonstrative POC app that I created just to show how we would view that internal data. However, you can use this to find any sort of internal data that's used by the app, and even cookie data and local storage data can lead to some rewardable vulnerabilities. And so to demonstrate that, let me walk you through how I have used this to escalate bugs from P5 to P4 to get a rewardable bounty. Now, obviously we're shooting for higher than P4 if we can, but this similar techniques can be used to find everything from P1s down to P4s. So a web app that does not terminate the user session upon logout on the server side only is a P5 bug, not rewardable. However, if that token is also not invalidated on the client side, that's a P4, which is generally rewardable. It's also low-hanging fruit, and so almost certainly would be a duplicate, but worth reporting usually. Similarly, you'll see that a sensitive token stored in local storage is also a P4. And we'll oftentimes see web apps that store session tokens in local storage, and that's a P4. And many times Android apps will use a simple web view to access a standard web page. And so some of the same bugs that you would find in a standard web app can be applicable to an Android mobile app. But the issue you encounter is, how do you demonstrate that the session token is not invalidated on the client side at logout if you can't view the internal data? Or how do you demonstrate that a sensitive token is stored in the local storage on the device unencrypted if you can't access the device the app internal storage? And so what this technique gives you is a way to gain exactly that access. And in that way, you can escalate a P5 to a P4, or potentially even find some P4s and higher that you would not be able to find otherwise. And of course, we're looking for more fruitful bugs than P4s. So what might you find that can be of more criticality? Well, in many instances, developers know better than to hard code sensitive tokens in the APK. And so you may not find them there, but they may have a need for some sort of token for a centralized back-end service. And if it's not implemented correctly, that may be a token that is shared between instances of the app. And so one common bug pattern that I see is the app will make an API call to a backend service, authenticate to that service, and receive some token, but that token is not individual to that instance of the app. It's actually a shared token to some backend service. And by having that shared token, you gain access to other users' data. Now, again, we may be able to find this, likely could see this if we were reviewing intercepted traffic, but we could also miss it. We could simply not see that request in Burp, or it could be obfuscated in some way, whether through encryption or compression. And so by being able to view the internal app data, we can see where the application has written that key down, sometimes in its shared preferences file, sometimes just in a random text file within its internal storage. But because the developer has the assumption that the attacker cannot access the internal app data, they have not applied any other security controls and have simply written that shared token to the storage in a clear text form that you can readily retrieve and then test with further techniques to identify more impactful vulnerabilities. So where can we get some of these tools? Again, I did not create any of these, but I came across them sometimes through other talks. Some of these I stumbled upon, but I did not create them. So it's important that we recognize those who have taken the time to generate these awesome tools that significantly reduce the workload for us bug bounty hunters. And we'll start with APK middle. So there's a GitHub here at Shrouded Code, and this is a Node.js package, so you do need to have Node running, obviously. And the GitHub repo there has a very nice walkthrough. Basically, once you have Node and the Node Package Manager, NPM, installed on your Mac or Linux device, and of course you can do this in Windows as well, you just run npm install apk middle and you're set. The others, you can get some of these tools through other means. I like to have them as jar files just because then it's very portable and easy to upgrade as they come out with other versions and stuff. And so what I found is these locations provide builds of the tools themselves as jars so that you don't have to mess with any of that. You just download the jar, run it with Java, and you're set. And then again, Android Studio, while you don't necessarily have to have the full Android Studio package to get the tools that we needed to perform our tasks today, I highly recommend that you get it and become familiar with it because it does provide a lot of other handy UI features and opens the door for you to start learning more and more about the Android environment and creating your own apps so that you can hack them and understand what the developers are going through. It's easy to be cynical of some of the mistakes that are made, but when you experience the challenges that the developers are trying to overcome, not only do you gain a whole new appreciation for how difficult it can be to implement some of the security features that we have come to expect, but you also learn what are some of the common pitfalls that developers encounter as they implement those security features. And of course, those translate directly into bug patterns that we can look for in our hacking methodology. I hope this was useful to you, and I look forward to talking to you again soon.